Hi everyone, welcome back to PRAKASAM tutorials. In my previous video, we have discussed about concept of moment generating function. Now here in this video, I am going to discuss about properties of moment generating function. And first property is, let capital X be a random variable, that is moment generating function random variable with moment generating function is mx of t. Then the moment generating function of a random variable capital Y is equal a capital X plus b is e power tb into mx of at. So this is the first property. So prove this property. So according to definition of moment generating function of a random variable is mx of t is expectation of e power tx. Now here we want to prove that moment generating function of the random variable ax plus b. So similar, this is the definition of moment generating function of the random variable capital X. So similarly, the moment generating function of the random variable capital Y is my of t is equal expectation of e power ty. Now here y is equal to ax plus b. Substitute y is equal to ax plus b into here we get my of t is equal expectation of e power t into ax plus b. Multiplying t within the bracket term we get RHS term is expectation of e power tax into e power tb. So using properties of expectation of ax is a into expectation of x. So now here e power tb is the constant. Using that property, expectation of e power atx into e power tb is written as e power tb into expectation of e power atx. So from the definition of moment generating function, expectation of e power tx is equal mx of t. So using this definition, so this expectation of e power at into x is mx of at. Expectation of e power atx is mx of at. So therefore, my of t is equal e power tb into mx of at. So this is the first property. And second property is mx of t is the moment generating function of the random variable capital X. Then the moment generating function of the random variable capital Y is equal to kx is mx of kt. Now prove this property. So we know that from the definition of the moment generating function of the random variable mx of t is equal to expectation of e power tx. Similarly, the moment generating function of the random variable capital Y is my of t is equal to expectation of e power ty. So now here y is equal to kx. Substitute y is equal to kx here in this equation on RHS side. We get my of t is equal to expectation of e power t into y is equal to kx. So this RHS term is written as expectation of e power tk into x. So using the definition of the moment generating function, expectation of e power tx is mx of t. So using this definition, expectation of e power tk into x is written as mx of tk, mx of tk or mx of kt. And that is the second property. And one more property of the moment generating function, if mx of t is the moment generating function of the random variable x, then the moment generating function y is equal to minus x is m suffix minus x of t is equal to mx of minus t. So that can be proved from this property, that is my of t is equal to mx of kt property. So as a special case, if constant k is equal to minus 1, substitute k is equal to minus 1 into this property, this equation. So now in this property y is equal to kx. So k is equal to minus 1. So m minus x of t is equal to mx of minus t. So this is the special case of the this property. That is one more property of the moment generating function of the random variable. So this property implies that if the random variable x has a density function symmetric about the origin, so then the moment generating function is also symmetric about the origin. Next, third property, if mx of t is the moment generating function of the random variable capital X, then the moment generating function of y is equal to x plus a by b is e power ta by b into mx of t by b. So similarly prove that this property. We know that from the definition of moment generating function of the random variable capital X is mx of t is expectation of e power tx. Similarly, the moment generating function of the random variable capital Y is my of t is equal expectation of e power ty. So now here capital Y is x plus a by b, and substitute this y value into RHS term of this equation. We get my of t is equal expectation of t into x plus a by b. So multiplying t within the bracket term, we get the RHS term is expectation of e power tx by b into e power ta by b. So e power ta by b is the constant. So using property of expectation of ax is ax. So using that property, the RHS term of this equation is written as e power ta by b into expectation of e power t by b into x. So using moment generating function definition, the value of expectation of e power t by b into x is mx of t by b. So therefore, my of t is equal e power ta by b into mx of t by b. So this is the third property. Next, fourth property is the moment generating function of the sum of a number of independent random variables is equal to the product of their respective moment generating functions. So that is m suffix x plus y of t is equal mx of t into my of t. So let capital X and capital Y are the two random variables. Then the moment generating function of the random variable x is mx of t, that is expectation of e power tx, and the moment generating function of the random variable y is my of t, and it is expectation of e power ty. So similarly, the moment generating function of x plus y is m suffix x plus y of t is equal expectation of e power t into x plus y. So expectation of e power t into x plus y is written as e power tx into e power ty. So now here random variables x and y are the independent random variable. So if the two random variables are independent to each other, so expectation of product of random variables is equal product of their individual expectation. So that is one of the property of expectation. Expectation of xy is equal to expectation of x into expectation of y. Expectation of product of random variables is equal to product of their individual expectation. So using that property, the RHS of this term is written as expectation of e power tx into expectation of e power ty. So from the definition of moment generating function of the random variable x and the moment generating function of the random variable y, expectation of e power tx is mx of t, expectation of e power ty is my of t. So therefore, m suffix x plus y of t is equal to mx of t into my of t. Hence, the moment generating function of sum of a number of independent random variables is equal to the product of their individual moment generating functions. That is, m suffix x plus y of t is equal to mx of t into my of t. This is the fourth property. Next, fifth property is if two random variables capital X and capital Y are two random variables with the moment generating functions are mx of t and my of t such that mx of t is equal to my of t, then capital X and capital Y are said to have identical distribution. So that is identical density. And sixth property is a random variable x may have no moments. Random variable x may have no moments even if its moment generating function exists. And seventh property is a random variable x can have its moment generating function and some movements or all the movements at the moment generating function does not generate the movements. Next property is the function k suffix x of t is equal to log e mx of t is called the cumulant generating function. So these are some important properties of moment generating function